So this is a work that has been done in collaboration with my guide Dr. R. Rajesh and Dr. Zabronsky. So in the title you can see there are two important things that we should notice. One is cluster aggregation, which is our system, and the other is rare events. So aggregation is an irreversible phenomenon, and it's present in many physical systems in one way or another. Biological systems, if you take protein clumping or blood coagulation, the first figure, this is, oh sorry, yeah, I don't know. Okay, you can see the first figure is the blood coagulation, second one is the formation of clouds, third is protein clumping, etc. on the left hand side. And what is aggregation? So we take two masses and they collide and stick together to form a bigger mass. So if masses m1 and m2 are colliding, they will form a bigger mass which has a mass m1 plus m2 with a certain rate which is proportional to what we are calling a collision kernel, and that is the k, which you can see on the schematic diagram. It's a function of the colliding masses. So the other part is rare events, right? So rare events we all know. Natural disasters is a very classic example of them, and of course we understand that they are infrequent, but it is very important to study because it could happen at any time and it has a significant impact. The first schematic diagram is the rare event in aggregation itself, where some misfolded proteins clump together to form what are called plaques in the case of causing neurodegenerative diseases such as Parkinson's or Alzheimer's. This one is for Alzheimer's. Okay. So the model is as follows. We have m particles of mass 1 initially. This is our system, and there are some collisions occurring. After every collision, there are multiple configurations which are possible. So in this figure, you can see there are 4 collisions occurring, and after every collision, there are many configurations. And because of this, there are many trajectories. So what do I mean by trajectory? From the first collision to the last, that is the 4th collision, there is a path of arrows, right? So every such path is a trajectory, right? And all the information about the shape of the colliding clusters or area of cross section or all these things, even the transport information, everything we have contained in this collision kernel K, which is a function of the masses, colliding masses. And the total mass m is always going to be conserved after every step. Okay. Now the important thing is, why are we studying this? Aggregation has been studied for more than 100 years now. The first study was done by Smoluchowski, I guess, in 1917, and he gave a differential equation for the typical Nm. What is Nm? The number of particles of a mass m. So that is what was described. So with this, we can find out the typical mass distribution for very few kernel choices, for very few k. Right? Some examples are the constant, sum, and product kernel. These are the most common and classic kernels which have been solved and exactly. And there is a very palpable lack of results for atypical results or atypical events or rare events in cluster aggregation. Just an aside, I mean, when I was working on these slides, I remembered around more than 10 years ago in Chennai, during, I think, summer or monsoon season, whatever, it was raining. But it suddenly turned into a hailstorm. We were on the road and we saw this. This never ever happens in Chennai. This is really a rare event. And it actually involves aggregation also. There are models which have been proposed for raindrop formation which use aggregation. So it could be a very direct application of. Okay, so the main question we are asking is this. So look at this plot here. It's a plot of the mean number of clusters. So what is N of t? N of t is the number of clusters which decay with time t, right? The red trajectory shows the typical way in which it decays. So I've marked on the y-axis, I've marked capital M and capital N. Capital M, as we said, is the initial number of monomers, which is just mass 1, which is M. And finally, the state is that whatever the configuration we may get, we are ending with n clusters. There will be a total of n clusters. That is what we want. So there are two conditions. Initial condition is that there are m particles of mass 1. Final condition is that there are n particles, or n clusters. Clusters is a better word. There are n clusters. Now, with these two constraints, there could be many trajectories possible. So our question is to ask, what is the probability that some trajectory like this is atypical, right? So the quantity we are looking at specifically is P of m and t, which is the probability of n particles remaining at a time t, given our initial condition. And what is P of m and t for atypical times? That is, what is the probability of such an atypical trajectory is what we are asking. And the results are as follows. We find that there is a large deviation function. Okay, so the probability P of m and t basically decays exponentially in the limit of large m, large total mass in the system, right? And under the condition that phi, which is the fraction of particles remaining, is finite, and also the scale time capital T is finite. Under these conditions, for any collision kernel you will take, there exists a large deviation principle, and there is a rate function associated with this principle, which is given by f of phi comma t. So, of course, this leads to the natural expectation that f of phi comma t should be 0 at the typical point, typical t, right? Because that would mean that P of m and t is maximum, right? So that also we find is true from our results. This is also true for all kernels, Kij. Apart from this, we have usually in large deviation calculations you could get the large deviation principle, but it is difficult to do that also. But even if you do that, solving it and getting the actual analytical form of the rate function, the f of phi comma t, is a little tricky. So, but we have managed to get it for the three classical cases, as I said, constant, sum and product kernels. And these are the results. So the first, from left to right, it's constant, sum and product kernels, and I have plotted f of phi comma t with respect to t. This t that I am talking about is scaled time. And I've plotted it for different phi's, 5.3, 0.5 and 0.5, yeah, and 0.8. And shown, the last line just shows the actual exact answers for each of these kernels. As we can see, at the typical time, this f of phi comma t goes to 0. We also find that the number of clusters decays. I mean, we find in principle first order differential equation for the decay of the number of clusters for any kernel again. Again, this can be solved exactly for the constant, sum and product kernels. This E is a parameter which, if E is 0, you would recover the typical case. And E could be positive or negative, and that would take you to either sides of the typical trajectory, long time or short time. So these are the so we are calling this instant on trajectory because of the way the calculation goes. I'm not going into that, but so these are the trajectories. The middle blue line shows in each plot, the blue line shows the typical trajectory, and the red and violet show the atypical trajectories. Check our results and make sure they're fine. We also developed an algorithm to access these atypical trajectories. This algorithm involves two moves. The first move is that I choose a certain collision and, choose a certain configuration and then just alter it so that none of the other configurations in the trajectory changes, right? So the trajectory is essentially changed only at a certain point, slightly perturbing the trajectory is what I'm doing. So it looks like this to visualize it. And the next move is that I choose a certain collision and change the waiting time. So, but in this case, since the waiting time changes, the total time taken for m minus n collisions would also change. That would also change. So this is how it looks. Yeah. We have checked that this algorithm is ergodic, and the results are here. We benchmarked it with the constant kernel because the constant kernel is the simplest case possible, right? Because in the constant kernel, k of ij is just 1. It doesn't depend on the colliding masses. So it is kind of easy to solve by hand. So we got P of M and T for that and benchmarked it with our simulation results also. And we find that this measures very low probabilities of 10 to the power minus 40, sometimes 60, depends. Sorry, so I would just like to go back and just point out something here. So, yeah, in this slide, so this is the, as I'll remind you, this is just the large deviation function for the constant sum and product kernels, and there are some expressions at the bottom. These expressions also very nicely give the asymptotic answers, as in the long time answers as well as the short time answers. So an interesting fact that you can note is that at the short time, for all three kernels, the f of phi t just goes as 1 minus phi into ln t. That's what it is for all three kernels. It just has a power law behavior with an exponent 1 minus phi. And of course, the long time behavior differs. That is there. Okay, so this is just a brief slide about the method of solution that we have. So we wrote a master equation for this quantity P of vector n comma t, which is just the probability of a certain configuration n in time t. And from there, we could write P of m and t, which is our quantity of interest, in terms of this P of n comma t, and rewriting it in a Schrodinger-like form, which has a Hamiltonian-like term coming in. We could exponentiate it and find, write it in a path integral form so that we could extract an action out of it. That action, after some algebra, etc., becomes the rate function. And some scaling also, then it becomes a rate function. So to summarize, we have basically developed an analytical formalism and a numerical method to study the tails of P of m and t, and we find that they match up very well. The large deviation function in principle is there for arbitrary kernels, but it can be solved for the classical cases of constant sum and product exactly. And we see that another check is that the Smoluchowski result is recovered at the typical time, which also we find to be true. And the equation for the instant-on trajectory for any kernel is an icing on the cake, which again, and there could be many directions in which this could be taken. One is to, again, obviously to study, use this formalism for other kernels, other collision kernels. We might need to do some approximations and some numerical magic, but yeah, it might be possible. And then aggregation, fragmentation process are also possible because it just involves one more term in the master equation. Maybe that could be possible. And instead of, and here we have not included, we have not explicitly spoken about any transport process. We just said that everything is contained in the kernel. We could try diffusive aggregation also, since that's a huge branch of aggregation. And instead of binary aggregation, we could go for k-nary aggregation and see if we can get some scaling loss there, whether a large deviation principle is available there also. Because one important thing that should be noticed here is, in many theoretical papers on aggregation, the form of the kernel which is taken is always homogeneous. Mostly, as far as to the best of my knowledge. But when we do the calculation, it doesn't, that form doesn't come in anywhere. We just keep it as Kij and we get some large deviation result. So whether that will, at some point, the homogeneity will affect the solution at some point is something to think about. So, thank you.
So you have, yeah, Jeremy, yes. Yeah, you go ahead. Yes.
Thank you for this very interesting talk. So maybe I missed something. So what are exactly the settings that you're putting in your aggregation process?
Can you repeat? Sorry?
What are the settings that you're considering in your aggregation process? Or in other words, settings. Yes.
Okay.
Or in other words, so basically, what are the source of fluctuations in your large deviations?
Settings as in.
No, so basically, are you considering a solution, directly a solution to the Smoluchowski equation?
So the Smoluchowski equation is recovered from this formalism. So we get an action, and at the typical point, we recover the Smoluchowski. When we minimize the action to find the Euler-Lagrange equations, etc., we end up with the Smoluchowski equation at the typical time.
But this is just a mean field equation for the average in principle.
Yeah.
So what is the source of fluctuation compared to this Molokhovsky equation that is giving the large deviations? It's a number of fluctuation. Okay, so it's a finite number. Okay.
Clusters as well as the trajectory, since this E is the parameter which controls what trajectory we look at. So depending on the value of E, we can get very, very rare trajectories and make them typical in some sense.
And then, what you assume, I guess, is some kind of well-mixing
Yes, we do.
condition that certainly you will lose when you are talking about non-homogeneous things.
Right, yeah.
Yes.
Thanks.
Yes.
So I was wondering whether you could extend that and constrain not just a overall number of clusters, but a sort of scaled version of the cluster size distribution, because then you could also get typical cluster size distributions.
Yeah, actually we can. That's another ongoing work.
Okay.
We can get the cluster size distribution. So I didn't show you the entire calculation, but the Zi bar and Zi, which is there in the last line, right? They are such that the Zi into Zi bar is Ni. That is your mass distribution. So we have also, for the constant sum and product kernels at least, we have got exact expressions for both Zi and Zi bar. Just multiplying them would give the mass distribution. We have to check it and other things, but it's ongoing work, yeah.
But what I was asking is whether you could constrain that, right? So here you're extracting the most likely cluster size distribution for a given phi, but you could maybe also constrain that, because then you can get your results by contraction, basically, right? And often putting more constraints in makes the calculation simpler. So,
yeah.
Sorry, in the action, where does the Kij come in?
Kij comes only in the E.
E, I see. And your m going to infinity limit goes through capital T.
Yeah.
Okay.
Yeah.
So you take the saddle point there and something like
Yes.
Sorry, what makes those three cases exactly solvable?
So just the form of the kernel. So the constant kernel was Kij is 1. The sum kernel is K. So the thing is, the rate of collision of mass I and j would actually be Kij into Ni into Nj, which is number of I and number of j. So what happens is that when you sum over, it either gives the number of clusters, total number of clusters, or the total mass, which makes it easier. Whereas if you had some I square or something, you would get the second moment of the number distribution. So you would get higher and higher moments, which is kind of hard to solve. We need to look for other methods. So, but these three cases are easily solvable.
Yeah, one more question from Arnab.
Yeah, Subashri, I was wondering, like in this case, right? So I understand the typical fluctuations in the large deviation. What would be the most atypical behavior? I mean, I'm trying to understand. It's like just one single cluster.
So no, we in our problem we have defined two constraints, right? So we start with m particles and end with n clusters. N is not equal to 1 because that's a totally different ball game. It leads to gelation, etc. So n not equal to 1. So in this, probably the most unlikely cluster could be the leftmost or rightmost path here. The rightmost, I would say, because there the one collides with the highest mass in each. 1 plus 1, 2, and then the next arrow is 2 plus 1, 3, next is 3 plus 1, 4. That kind of thing happens. That could be the most unlikely path. But I don't know, we could check that, of course. That can be done.
see that in the rate function,
Yeah.
but it's higher.
Yeah, we can see that. Yeah. In fact, I would say that it is rare because when we try to asymptotically calculate for the product kernel or sum kernel, right? This is the trajectory path that we assumed in our calculations. It was we guessed somehow, and that gives the right asymptotic answer also. So at large times, that is the rarest configuration. That is, it coincides with the large deviation function. So that is pretty rare.